Welcome back. This will be a video lecture on section 1.3, lines and planes. This will be the first half of a two-part series on section 1.3. I've got section 1.3 broken down into 6 pieces, and we will do the first 4 of these as part A, and we'll do these last 2 pieces as a part B. So in part A, we're going to have lines. We're going to be talking about lines in space in 2 different ways, normal forms and vector forms. And then we'll be doing the same thing for planes in 3-dimensional space. We'll have a normal form and a vector form. We're going to save distance problems and the cross product for part B on section 1.3. So let's begin with lines, normal form. Now when we think of a line in normal form, we're thinking of a line that's being generated by 2 pieces of data. All right? Let's look at this. Let P be a vector in R2. So P is a vector on the plane. I've got one pictured here below. This is the red vector here. And let N be a non-zero vector in R2 called a normal vector. So let's think of these as 2 pieces of data. These 2 pieces of data are going to generate our line. And here's how we're going to do that, right? Describe the set of vectors x in the plane whose displacement from P is orthogonal to N. In other words, we're going to admit a vector x into the set if I draw the vector x, I compute the difference between x and p, so I compute x minus p. If that generates a displacement, if x minus p is orthogonal to n, I'm going to keep that vector. But if I generate a vector and x minus p is not orthogonal to n, I'm going to disregard that vector. So what would be the set of vectors that we would admit? Right? What kind of set would they generate? So let's do a test. All right, I'm going to give you 2 pictures here, right? So take a look at the picture on the left. If I asked you to draw in the vector x minus p, is it orthogonal to n? If it is, we're going to keep that vector x, and if it's not, we're going to disregard it. All right, take a look at the picture on the right. Same thing. We're going to take that vector x, we're going to draw in the displacement x minus p. If that displacement is orthogonal to n, we're going to keep x, and if not, we're going to disregard it. So think about both of these situations, right? Let's go back to the one on the left. So if I draw in x minus p, I'm picturing a vector that starts at p and ends at x. Okay, so it's going to be this vector here. And when I draw that, it doesn't look like it's orthogonal to n. So this would not be a vector that gets admitted into the club, so to speak. Now let's take a look at this situation. If I draw in x minus p, so if I start at p and direct myself towards x, that displacement does look like it's orthogonal to n, so I would keep this vector. Now, take all the keeper vectors, take all the ones that satisfy this condition, and imagine the set in the plane that their tips trace out. Okay? Hopefully, you're seeing this picture, right? All of the tips of the vectors x that are admitted into this club are going to trace out this beautiful blue line here, right? So here's a typical x, right? Here's a typical x that's admitted, right? X minus p is this yellow vector. The yellow vector is orthogonal to the normal vector, the green vector. And since it's orthogonal, we're going to keep that value. And if we could look at all the vectors x that we've kept, they're going to trace out this blue line. So we can think of that blue line as the line that's created from these 2 pieces of data, the vector p and this normal vector n. So an important thing to remember in this discussion is that the tip of this vector x is sitting on this blue line, provided that x minus p, this displacement, is normal or orthogonal to n. And that means that the dot product of n and x minus p is equal to 0. So let me say that again. This vector x, the tip of this vector x is going to be on the line if and only if n dotted with x minus p is equal to 0. And so that's what gives rise to this definition, right? The normal form of the equation of a line L in R2 is n dotted with x minus p equals 0. Now remember, n is given to us, that's the normal vector. P is given to us, that's a position vector. That's pointing to a point on the line. And so this is really a test for these vectors x. The vectors x that satisfy this equation, the tips of those vectors are going to be on the line. Now, by distributing the dot product across this difference and rearranging the terms, we can render this as n dotted with x is equal to n dotted with p. So I would accept either one of these. These are essentially the same equation. Those are what we would call the normal form of the equation of a line L, and these are stated in terms of vectors. Now I will show you through some examples how we can take this vector form and reduce it down into what's called the general form of the equation of a line L, which is typically written as something in the form ax plus by equals c. Now, we can reverse, I'll show you how to do this, but we can reverse engineer. If we saw an equation of a line in this general form, we can abstract out of this equation the normal vector. The normal vector is always going to be obtained by grabbing the coefficient of x and the coefficient of y and tucking those in as the components of the normal vector. So our normal vector can be abstracted right out of this equation. So we can always recover the normal vector from the general form of the equation that's given to us. Now, a good way to get into this, a good way to start thinking about this, is to just look at a couple of problems. So we'll take these two problems with us over to the document camera, and we'll solve them. And hopefully by the time we're done solving these problems, we'll have a very good grasp of how the normal form of the equation of the line works. So join me over the document camera for the solutions to these two problems. All right, welcome to the document camera. Let's work this first problem together. Now we're going to let x denote a generic vector in R2. So let's let x stand for the vector, let's say with components x and y. So we could write it as a column that way or as a row this way. All right, and our equation, the equation for the line from this data, is going to be x minus p dotted with n equals 0. Now, by distributing the dot product over the difference and moving the n dot p to the other side, this, of course, is equivalent to n dot x is equal to n dot p. All right, let's do some calculations. If I take the normal vector and I dot it with x, let's see what we're going to get. We've got negative 5, 4 dotted with x, y, and that's going to give us minus 5x plus 4y. So we've got that side done. Let's do n dot p. Negative 5, 4 dotted with 2 comma negative 3. And that will be a negative 10 minus 12, which is negative 22. So the equation of our line, which is given by this relationship, is going to be negative 5x plus 4y is equal to negative 22. And that's what we would call the general form. So we would call this the normal form. And we would call it, when written this way, as our general form for the equation of the line with this data. Okay, let's try this second problem. Find a position vector p and a normal vector n that produce the line with this general equation, right? 3x plus 4y equals 12. Well, by reverse engineering this process, one thing we know immediately when we see this general form is we can pick out the normal vector. The normal vector is going to have coefficients or components 3 and 4. Now, in principle, any point on the line can serve as the tip of the position vector p. So we just have to find a point on the line. And it's pretty easy in this case. There's several what I would call natural candidates for a point on this line. So if we want to think about it geometrically, when I set x equal to 0, I can see that y is equal to 6. And when I set y equal to 0, I can see x is equal to 8. So I can find these two intercepts. And so a couple of natural candidates for p. One natural candidate would be p is the vector with components 0 and 6. So that's equivalent to choosing that vector. Or I could have p equal to 8, 0. That would be another natural choice. So those are two that kind of naturally suggest themselves. Of course, any point on this line will do the job. So if you can just find any point by hook or by crook, you can use that as a position vector. So if you take this normal vector with this position vector or with this position vector, either way, you're going to generate this equation. So we can, basically this was just an exercise in seeing the general form and seeing if we could lift out of it the information, the normal vector and a position vector that would generate this general equation. Okay, so that brings a conclusion to this problem. Let's go back to the class notes. We say that two lines in the plane are parallel, provided that their normal vectors are parallel. And we say that two lines in the plane are perpendicular, provided that their normal vectors are orthogonal. Now that draws a conclusion to our discussion of lines in the normal form. Now we're going to want to talk about lines in vector form. And one of the things that we're going to see by looking at lines in this vector form is that it will allow us to talk about lines in higher dimensions. So we can lift the idea of line out of the plane and talk about lines in three-dimensional space, or in general in n-dimensional space. So let P be a vector in the plane, and let D be a non-zero vector in the plane. Describe the set of vectors x in the plane whose displacement from P is a multiple of D, or equivalently, is parallel to D. So we have a condition that looks like this now, right? If I hand you a vector x, what you're going to do is you're going to calculate the displacement from x to p. So you're going to calculate x minus p, and you're going to ask, is x minus p parallel to D? If it is, you're going to keep the vector x, and if it's not, you're going to throw it away. And then if you look at all the vectors we've kept and you look at their tips, they're going to trace out some figure in the plane, and that's going to be the line determined by P and D. So this is a little bit like what we did with normal vectors, except now the condition is that x minus P is parallel to D rather than perpendicular. Okay? So can you picture the line that's generated by this vector P, this position vector, and this direction vector? All right. As before, let me give you a couple of scenarios here, right? So let's take a look at this picture on the left. If I look at this vector x, do I want to keep this one or do I want to throw this one away? Well, the acid test, the test for whether we keep it or throw it away is the displacement from P. So is x minus P parallel to D? So think about that picture. And let's go over here. Should I keep this vector or should I throw it away? Well, let's take a look. I look at x, I look at P, I compute x minus P, and I ask myself, is this parallel to D or not? If it is, I'll keep it. If it's not, I'm going to throw it away. Well, let's go back to this one. If you've had some time to think about this picture, hopefully you've come to the conclusion that this one looks like I should keep it because x minus P looks like it's parallel to D, so I'm going to keep this one. This one I hope you agree you should throw away because if I look at x minus P, it does not look like it's parallel to D, so I should throw this one away. So if you're thinking about the line that's generated from P and D, I hope you've come to this picture, right? Here's a typical x that works, right? I take this vector x, I look at x minus P, that's this vector that's drawn in yellow, and it's parallel to D, so I'm going to keep this vector x. And if I look at all the vectors x that I would keep, they're going to be the tips of those vectors are going to form this blue line. So that's the line, that blue line is what's generated from this data, this position vector P and this direction vector D. Now this leads us naturally to the vector form of the equation of a line. So here's the definition. The vector form of the equation of a line L in the plane, or even in higher dimensional space, is x equals position vector plus multiples of the displacement vector. This is equivalent to saying that x minus p is a multiple of the direction vector d. And so remember that p is a specific point on the line and d is a non-zero vector, which is the direction vector or the direction of the line. Now the equations corresponding to the components of the vector form of the equation are called the parametric equations of the line. So the thing to remember here is that this value of t is a scalar quantity. It's any real number that I want, and as I sweep through all those values of t, I'm going to sweep out the line. And so this is the underlying parameter for the parametric equations. Now, this is best understood in the context of working out an example. So what I want to do is work on a couple of problems for you where we work out equations for lines, 1 in 2-dimensional space and 1 in 3-dimensional space. And I think you'll notice that the meaning and form of these parametric equations comes naturally out of the vector form of the equation of the line. So join me at the document camera. We'll take a look at these problems 1 and 2, and hopefully you'll come out on the other side of that experience with a pretty good grasp of how to construct and interpret lines in this parametric and vector form. All right, welcome back to the document camera. Let's work parts 1 and 2 of this problem. In each case, find the vector and parametric forms of the line passing through the vector p with the direction d. All right, now we know that in general, let's write it up here, right, that the line is going to have an equation of the form p plus t times d, where t is a parameter. We can set that value of t to be any real number. Okay, so that's our parameter. We can just basically choose different values of t, and that's going to pick out different points on the line. It's going to point to different points on the line. Okay, now it's going to be easier to work with this if we write our vectors in columns rather than rows. You'll see why. That naturally lends itself to the parametric form. So let's write this. Let's write out the vector form of our line with using column vectors instead of row vectors. So in case 1 here, we'll have 1, 2 plus t times 2, 3. This is some scalar. So let's do the scalar multiplication and the vector addition. And this is what I would call the vector equation of the line. Okay, this is our vector form. Now when we want to write it in parametric form, all we have to do is we have to just think of this as producing a vector with coordinates x and y. So all we do is we think of this as a vector with coordinates x, components x and y. And we say, all right, x is equal to this and y is equal to this. And so we write those as separate equations. And when we write them as separate equations, one for x and one for y, this is what's usually called the parametric form of the equation of the line. And this is what we would call our vector form. Although technically this could also be considered the vector form. So either this or together, the form where we put it together. Either of those could be called the vector form. All right, let's repeat this now, this time in dimension 3. So one nice thing about writing equations of lines using a vector p to position the line and a direction vector d is that it works in 2 dimensions and 3 dimensions. So let's repeat this now. So our vector form is going to be our position vector plus multiples of the direction vector. Now by scaling, and then by doing the vector addition, we can see that the components of this vector are going to be -1 plus 4t, 4 minus 3t, and 2 plus t. And again, we can think of the point on the line that this is generating as having coordinates x, y, and z. And so we would think of this as our vector form, but we can look at it component by component and write out the corresponding parametric form. So our parametric form would be 3 equations, one for x, one for y, and one for z. And it would be x equals -1 plus 4t, y equals 4 minus 3t, and z equals 2 plus t. Okay, so again, this could be our vector form, or we could think of this as the vector form, and this would be our parametric form. All right, so let's go back to the class notes and continue. So I want to work another problem with you involving vector and parametric forms of lines. Now, in this first problem, we have to construct the vector and parametric forms of the equation of the line using only a pair of position vectors. So we're not given a direction vector. So one thing you can think about while we're heading over to the document camera is if I just give you a pair of position vectors, in other words, if I give you 2 points on the line, how would you find the direction vector? Okay, so think about that as we head over. So I've got P and Q are both in some sense position vectors on this line. So our first task is to generate the vector and parametric forms of the line based on that data. And then in part 2, I'm telling you something about one of the points that this line is passing through. I'm telling you that the y coordinate of a point that this line is passing through is 10. And from that, you have to pull out or extrapolate the x and the z coordinates of that same point. So this is a way in which we can use the parametric form of the equation of that line to help us solve a problem like problem 2. So let's go over to the document camera. We'll work these problems 1 and 2 in detail, and hopefully we'll have a richer sense of how we can use those parametric equations to solve problems. Welcome back to the document camera. In this problem, we have a line in R3 passes through P with components 1, 2, 1 and Q with components 6, -2, 3. Our first task is to find the vector and parametric forms of the line. Now you'll notice in this case, we don't have a direction vector. We have 2 vectors that sit on the line or whose tips sit on the line. So our first step is to manufacture the direction vector, and we can do this pretty quickly if we just think about the situation. So these are not supposed to be accurate representations of the vectors P and Q, but just for the purposes of kind of thinking our way through this problem, let's imagine we've got P and we've got Q and we've got the line between them, or the line that's generated by those 2 points. All right, so this is the line. We're trying to get the equation of that line in vector and parametric form. So we need a vector to serve as the direction vector. And here, there's a couple of natural choices, right? I think it helps to think about the vector that goes from P to Q as a natural candidate for a direction vector. We could also think of the vector that points from Q to P, but let's use this one that I've pictured here. And so that would be the vector Q minus P. So a natural candidate for D here is the vector Q minus the vector P. And let's work that out. Q has components 6, -2, 3. And P has components 1, 2, 1. So the direction vector would have components 5, -4, and 2. Okay, so our line has this direction. We need a point on the line, or a vector that points to a point on the line, to serve as our position vector. And we can use either P or Q. Either one of these would work. Let's go ahead and use P. So our vector form is going to start with the position vector 1, 2, 1, together with multiples of the direction vector. So in vector form, we could write this as 1 plus 5t, 2 minus 4t, 1 plus 2t. Okay, and if we're thinking about this as a generic point on the line, we'll call it x, y, z. we can think of this as the vector form of the equation of the line. This will give us all the vectors whose tips lie on this line as we sweep that value of t. Okay, now we want to write the parametric forms of the line, and all we have to do is just write out component by component. X equals 1 plus 5t, y equals 2 minus 4t, and finally z equals 1 plus 2t. Okay, so there's our parametric form for the equation of the line generated by P and D. All right, let's take a look at part 2. The line passes through a point whose y-coordinate is 10. What are the x and z coordinates of this point? So we know that at some point, this line is passing through this point, and the y-coordinate of that point is 10. And now we have to find the corresponding x and z coordinates. Now, one way to do that is to realize that once I tell you that the point has a y-coordinate of 10, that's equivalent to telling you that 2 minus 4t is equal to 10. So let's write that down. Y equals 10 implies 2 minus 4t equals 10. And once I know that, this is a simple equation to solve for t. And once I know the value of t, that's going to allow me to find the values of x and z. So let's just solve this equation. This is equivalent to saying 4t is equal to negative 8. Or t is equal to negative 2. So the point in question is happening when t is equal to negative 2. So now all I have to do is plug in negative 2 here and here. Let's do that. So at t equals negative 2, x is equal to 1 plus 5 times negative 2, 1 minus 10, or negative 9. And z is equal to 1 plus 2 times negative 2, or 1 minus 4, or negative 3. So our point is going to have coordinates negative 9. We said y was equal to 10. That's what got the ball rolling. And z was equal to negative 3. So there's our point. It must correspond to that point there. All right, so hopefully that allows you to see how the parametric form can be used to solve for the other two coordinates when one of the coordinates is known. So we've got the vector and parametric forms of the line, and we know, given one of the coordinates, how to find the other two. All right, excellent. Let's go back to the class notes and continue. So two lines in n-dimensional space are parallel, provided that their direction vectors are parallel. And two lines in n-dimensional space are called perpendicular, provided that A, they intersect, and B, their direction vectors are orthogonal. So we have to be a little bit careful here in higher dimensions once we get beyond dimension 2. The direction vectors might be orthogonal, but the two lines might not intersect with each other, and so we would not want to call those lines perpendicular. So perpendicular lines must intersect, so they have to share a common point, and their direction vectors must be orthogonal. So that's one thing that we have to be careful of when we move the idea of lines into higher dimensional space. Okay, that's the end of lines in vector form. Our next topic is planes in normal form in three-dimensional space. Now, our treatment of planes in three-dimensional space under the normal form mirrors our treatment of lines in two-dimensional space under the normal form. So let P be a vector in three-dimensional space, and let N be a non-zero vector in three-dimensional space called a normal vector. So as before, P is going to point to a specific point in the plane, and using that point and this normal vector N, we can generate all the other points in the plane. So we want to describe the set of vectors X in R3 whose displacement from P is orthogonal to N. And I've got such an X drawn here in this picture below, right? I've got a vector X, and it has the quality that when I look at X minus P, when I generate this yellow vector, that's at a right angle to or is orthogonal to n. Now, when I collect all of the tips of these vectors x, it's going to generate this pink plane in three-dimensional space. So we should think of P, that's going to give us a point, a specific point in the plane, and n as the data for the plane, right? So I have a point, I've got a normal vector, and from that, I can generate all of these pink points using the property that n and x minus p are orthogonal to each other. Now, if we think about what that means mathematically, that means that the dot product of n and x minus p is equal to 0. And so that's what leads us to our next definition. The normal form of the equation of a plane P in R3 is n dotted with x minus p equals 0. So given n and p, I can test all the other vectors x through this equation. If a vector x satisfies this equation, then we throw its tip into the plane. And if the vector x doesn't satisfy this equation, we don't include it. Its tip is not included as part of the plane. Now, by using the distributive law, we can easily rewrite this equation as n dot x equals n dot p. So this is just what we did with lines before. Okay, now I'll show you through example. It's easier to talk about this by looking at a specific example, but anytime we start with this normal form, we can easily generate from that something called the general form of the equation of a plane, and it just takes on the form ax plus by plus cz equals d. So in other words, it's just like the general form of the equation of a line in two-dimensional space, where we now have just the added piece denoted by c dot z in this case. Now, as we saw with lines, if someone hands me the general form of the equation of the plane, I can also abstract out of this equation the normal vector by simply pulling off the coefficients of x, y, and z and making them the components of a vector, which will coincide with the normal vector that generates that plane. So given the normal form, we can generate the general form, and given the general form, we can abstract the normal form. Now, what I want to do is look at some problems here where we play with this normal form for the equation of a plane. So join me at the document camera and we'll work out this problem in detail. Welcome back to the document camera. In this problem, we are going to find the equation of the plane in normal form that passes through the point 1, 3, negative 2 and has normal vector n equals negative 2, 3, negative 4. Now, let's just write down some information here. We're going to think of the vector that starts at the origin and terminates at this point. We're going to call that vector p. So let's think of p as the vector with components 1, 3, and negative 2. We have our normal vector, negative 2, 3, negative 4. And we want to identify a generic vector that's going to sit on this plane. So let's call that vector x. And let's say its components are x, y, and z. Now there's a couple of different ways to think about the normal form. So one way to think about it initially is to say, well, we're looking for all the vectors such that x minus p is orthogonal to n. So x minus p is orthogonal to n would translate into n dotted with x minus p is equal to 0. But by the distributive property and some basic arithmetic, we can write this as n dotted with x is equal to n dotted with p. So either one of these could be considered the normal form. This one's a little easier to work with. So we can see that we've got two calculations to carry out. So let's carry out these calculations. We want to get n dotted with x on the left-hand side, and so we can see that right here. We're going to have negative 2x plus 3y minus 4z. That's our left-hand side. And then we've got to do n times p. And that's going to be up here, right? We're going to have negative 2, 9, and 8. And so we're going to have what? That'll be 15. Okay. So we just have to equate them now. So the equation in general form for our line is going to be negative 2x plus 3y minus 4z equals 15. And that gives us the equation of our plane in general form. All right, that takes care of this problem. Let's head back to the class notes. Welcome back. Now I want to work a problem where we have to find the equation of the plane that is tangent to the sphere x squared plus y squared plus z squared equals 169 at the point with coordinates 3, 4, and 12. So join me at the document camera and we'll take a look at this problem. All right, welcome to the document camera. We want to find the equation of the plane in normal form, and we'll do it in general form, that is tangent to the sphere x squared plus y squared plus z squared equals 169. So that would be the general equation for a sphere of radius 13 in three-dimensional space. And at the point 3, 4, 2, so we want to find the plane that's tangent to the sphere at this point. And by just plugging in 3, 4, and 12, you can see that that's going to satisfy this equation. So this is a point on the sphere. So we have a point. Let's call this, let's call the vector whose tip sits at 3, 4, 2. Let's call that vector P. So P is going to be the vector whose tip sits at 3, 4, 12. The thing that we're missing in this is we need to know the normal vector for this plane. And we can borrow an idea. It's absolutely true for the sphere, and it's an idea that we can borrow from the circle. So let's just remember this fact from the circle, right? When I have a circle centered at the origin, if I take any point on that circle at all, and I think about this vector, the vector that starts at the origin and terminates at that point, that's always going to be normal to the line that's tangent to the circle at that point. So in other words, the normal vector that we need is the vector that I get by simply using the vector 3, 4, 12. Okay? So our normal is just going to be the vector that starts at the origin and points to this point. Okay? So that's the data that we need to solve this problem. So now all we have to do is write out the equation n times x equals n times p. Now let's remember our vector x is going to be a generic point, a vector with components x, y, and z. And so we just have to write out the equation n dotted with x is equal to n dotted with p and work out the details. So let's do that here. So n dotted with x is going to be what I get when I take the dot product with these two vectors, n and x. So we're going to get 3x plus 4y plus 12z. And when I do n dotted with p, we're going to get the dot product of these two vectors. So we'll get 9, 16, and 144. And that's going to be 169. Okay? So our final tangent plane, the plane that's tangent to our sphere at this point, is going to be what I get by setting the n dot x equal to the n dot p. So our plane is going to have general equation 3x plus 4y plus 12z equals 169. And that's the solution to the problem. So the big idea here is that for a sphere, just as for the circle, if I take the vector that points to my point, right, in that case, this vector 3, 4, 12, that's going to be a normal vector for this tangent plane. Okay, so I hope you enjoyed that problem. Let's head back to the class notes and continue. Now, as with lines, we can easily talk about what it would mean for some planes to be parallel or perpendicular. So we'll say that two planes are parallel, provided that their normal vectors are parallel, And we'll say that two planes are perpendicular provided that their normal vectors are orthogonal. Now I want to work a problem with you where we look at a pair of planes and we have to decide whether or not they're parallel. And then we want to find the line of intersection of the two planes. So join me at the document camera to look at this, look at the solution to this problem in some detail. Welcome back to the document camera. In this problem, we've got two different planes under consideration. We've got a plane P1 with this equation and a plane P2 with this equation. And our first task is to show that these planes are not parallel. So what we have to do is we have to abstract the normal vectors out of each of these planes, and we need to compare them. Are the normal vectors parallel or not? Well, let's find out. It's relatively easy to abstract the normal vector out of the general form of the equation. We can simply look at the coefficients of x, y, and z and make those the components of the corresponding normal vector. So this plane has normal vector, let's call it n1, with components 1, 2, and -3. And the second normal vector for plane 2 has coordinates or components 3, 8, and -13. And the question is, this is the question of parallel, right? So they're parallel if and only if I can find a multiple of one of the vectors to get me to the other vector. So we would say maybe they're parallel if I can think of writing n2 as some constant a, some scalar a times n1. Can I scale n1 to get it to n2? Now let's see. If I scale n1 by a, that's going to raise all of these, that's going to multiply all of these components by a. So it'll be a, 2a, and -3a. And they would have to be component-wise equal to 3, 8, and -13. So we would get three equations that would have to be simultaneously true. Namely, 3 would have to be equal to a. 8 would have to be equal to 2a, and -13 would have to be equal to -3a. Well, let's see if this is even possible, right? If a is equal to 3, right, we can use equation 1 to assert that a is equal to 3. And if I plug that into equation 2, we would be left with 8 is equal to 2 times 3, which is 6, which is a contradiction, all right? That's a contradiction. Right, we're led to an absurd conclusion. And that means that this solution is not consistent. It's what we would call an inconsistent system. And there is no value a that can simultaneously satisfy all of these conditions. The long and short of it is, there is no way to scale n1 to become n2. So we would say that n1 and n2 are not parallel. Okay, so that satisfies the first part here. We know that these planes are not parallel. Now what we want to do, and this is true of any pair of non-parallel planes, two non-parallel planes have to intersect in a line. All right, you can kind of think of a picture here. It's kind of hard to draw these pictures, but you can imagine a picture something like this. You have to imagine these planes kind of extending in space. But you can kind of see this one plane and another plane intersecting in a line. And that's what we're trying to find. We're trying to find the equation of that line L. Now, what would it mean to say to find the points where the two planes intersect? That means we're looking at these general equations. I want to make sure I transcribe them carefully, because if I make any mistakes along the way here, it's all for naught. What that means is we're looking for simultaneous solutions. We're looking for x, y's, and z's that satisfy this equation that puts you on plane 1 and this equation, that puts you on plane 2. And so a point on the line here, a point that we're looking for is a point that's both on plane 1 and simultaneously on plane 2. So we're looking for simultaneous solutions to this system of equations. Now, we're going to have much better techniques for doing this by the time we get into chapter 2, but for now, let's just kind of use our, let's match coefficients and add and subtract these equations to try to drop one of the variables out, and we'll see that that actually works rather successfully in this case. So I think what's a winning strategy here is to pick on this x here. Let's take this first equation and multiply both sides by 3 and replace it by an equivalent equation, this one with 3x plus 6y minus 9z equals 3 times 19, which is going to be 57. Okay? So we're basically replacing this old equation 1 with this new equation 1. So let's temporarily kind of blot this one out. We've replaced it by something else. Okay? Now, if we look at these two equations, I can take equation 1, right? I can take equation 1 and I can subtract equation 2. So let's label these. Let's label them 1 and 2 now. I'm going to take equation 1 minus equation 2. And on this left-hand side, the 3 x's will cancel, so there'll be no x. I'll have 6y minus 6y minus 8y, so that's minus 2y. I'll have minus 9z minus a minus 13z, so that's minus 9z plus 13z, that's going to be plus 4z. And then I'm going to have the 57 minus the 73, that's a negative 16. Okay, so by taking this equation 1 and this equation 2, and by subtracting them, I drop the x out, and I now have a relationship that says negative 2y plus 4z equals negative 16. All right, now I'm going to take this equation and simplify it. I'm going to divide through by negative 2 just to kind of clean up the coefficients a little bit, and we're going to get y minus 2z equals 8. And then I'm going to solve this for y. All right, and this is where I want to kind of end the first phase of this argument. So I've used the two equations, I've eliminated one of the variables, and now I've solved for y in terms of z. Okay, now here's the second phase of the argument. I want to go back to, it doesn't matter which equation we go back to. We can go back to, let's go back to the one I've circled here, because it's got just x sitting by itself. I want to go back to this equation now. I want to substitute in place of y. I'm going to put 2z plus 8 in place of y here, and then I want to get a relationship that relates x to z. I can do that once I replace y by 2z plus 8. So my goal is to substitute and then write x in terms of z. All right, so let's do the substitution part. So according to this equation, x plus 2 times 2z plus 8 minus 3z equals 19. Okay, now let's keep going. X plus 4z plus 16 minus 3z equals 19. Now let's get x by itself. We can bring the 16 over. I can write 4z minus 3z as z, and I can bring that over. And so we're going to get x is going to equal, it's z on this side, so minus z plus 3. Okay? So now this is kind of phase 2. So phase 1 was getting y in terms of z. Phase 2 is using back substitution to get x in terms of z. And we just have to acknowledge that z is kind of free to be whatever it wants to be. Z in some sense is going to end up being the parameter for our line. So one way to think about it, we're going to write out a general solution here right now, but if you're trying to figure out how z comes into this problem, every time I pick a different value of z, it resets the value of x, it resets the value of y, and it generates a new point on this line. So as I sweep through the values of z, it's going to run along this line and sweep out different values for points on that line. So here's a phase here's an intermediate phase that's helpful to go through. I'm going to make a set of stacked equations. I'm going to start with x, and I'm going to write y. And then this last one, it looks silly to do this, but I'm just going to write it, z equals z. So think of this as like a parametric equation, a parametric form for your line. Now let's write it in vector form. And now let's separate it out into a position vector and a scalar times a direction vector. So this is how the line will finally reveal itself to us in this vector form. I'm going to separate this out into a 3, an 8, and a 0. Plus z. Z is going to be my scalar multiple of a direction vector, which is going to be -1, 2, 1. Okay, and now we know we're looking at a line. This is how we know we're looking at a line, because we've got a point, all right, a position vector that's pointing to a point in space, plus a scalar multiple of a direction vector. So this is, in kind of generic terms, this is our vector p, that's our vector that positions our line in space, and this is normally what we call the direction vector d, and this is our scalar, our parameter in this case. Okay, so z is acting as our parameter. As I change the value of z, it's producing different points on our line. Okay, so this is kind of a nice plug for why we want to be able to think about lines in space, both in kind of parametric form, general form, and vector form, because you just never know which one's going to kind of appear to you. So this problem started out by looking at a pair of planes in general form and working out the intersection of those two planes. We're trying to find the line that forms the intersection of these two planes. And lo and behold, what's helpful for us in this case is to have the vector form of the equation of the line at our disposal, so we can see right there that we've got a line that's determined by a position vector and a direction vector. So it's a nice plug for having the vector form equation of a line at our ready, at our beck and call, if you will. Okay, that brings this problem to a conclusion. Let's go back to the class notes and continue. In this subsection, we're going to look at another way of describing planes in three-dimensional space, and in this case, it's the vector form. So let P be a vector in R3, and let U and V be non-zero and non-parallel vectors in R3. And we're going to think of U and V as direction vectors. So the way we're going to be thinking about this is that P is going to get us onto the plane. So P is pointing to a point on the plane. And I'm going to generate all the other points in the plane by allowing myself to move away from P, not just in one direction, but in two directions. So I can move away from P using both the directions U and V, and in truth, linear combinations of U and V. So I can direct myself away from P using U and V and all of their various linear combinations. So what would it mean for a vector x to have its tip sitting in the plane? Well, it would mean that x minus p, that difference, that displacement from p, is a linear combination of u and v. So another way of saying that is x is going to be of the form p plus a linear combination of u and v. And that's what motivates our next definition. So the vector form of the equation of a plane P in R3 is a vector x of the form P plus a linear combination of u and v. In other words, P gets us onto the plane, and we can move to other points in the plane by forming linear combinations of u and v. And that's how we get to other vectors on the plane x. All right, Now, we'll work some examples where we take the data P, U, and V, and we generate the so-called vector form of the equation of the plane. That's actually very easy to do if P, U, and V are given to us. But then I'll show you how we can take that vector form of the equation of the plane and turn it into the so-called the associated parametric equations of the plane. That's a very simple process. It mirrors what we did with the vector form of the equation of the line and its associated parametric equations. So that's very easy to do, and that's best described by looking at an example. So let's begin with this example. I'm going to give you a point in three-dimensional space P and a pair of direction vectors U and V. So let's head over to the document camera and let's put together both the vector and parametric forms of the plane in R3 generated by this data. All right, welcome back to the document camera. In this problem, we are going to find the vector and parametric forms of the plane in three-dimensional space passing through this vector P and with direction vectors given by U and V. Now, this is really just a matter of assembling the pieces because we know that in general, we just have to take our position vector P and add on multiples of our two direction vectors. So there's going to be two different parameters that we'll have to work with, S and T. And by setting different values for S and T, we're going to be picking out different points in the plane. All right, so now we just have to kind of generically plug in our specific data. So this is going to look like, I'm going to write it as columns here, 1, 1, 3, S times U, so that's 4, 2, negative 5, and T times V with coordinates or components, negative 1, negative 2, 6. Okay, now we have to scale all of these components by S. We have to scale all of these components by T. And then we have to do our vector addition. Now, that's going to result in a first component, which is going to be 1 plus 4S minus T. In our second component, we're going to have 1 plus 2S minus 2T. And then finally, we'll have 3 minus 5S plus 6T. And we can think of the generic vector that's determining as having components X, Y, and Z. All right, so we'll call that vector X. So a generic vector X on the plane is of this form, where we think of S and T as just any real numbers whatsoever. Just pick any pair of real numbers, S and T, plug them in, and you're going to generate a point on this plane. Okay, now that's the vector form, right? Everything is expressed in terms of vectors. The point on the plane that's determined by, I should say, the vector that's determined by the point on the plane is of this form. Okay, now we want to find the corresponding parametric form. And all we have to do is rip this apart and think of this as a set of equations, one for X, one for Y, and one for Z, just by comparing components. So the parametric form is just a matter of equating. So X equals 1 plus 4S minus T. Y is equal to 1 plus 2S minus 2T. And Z is equal to 3 minus 5S plus 6T. And so we would think of these as our parametric equations for that plane. And again, S and T are just any real numbers. Any pair of real numbers is going to generate some new point on that plane. Okay, so working with these vector and parametric forms for planes is not that different than working for the vector and parametric forms for lines. It's just instead of having a single parameter, right? If we had a single parameter, we would be generating a line. If we have a pair of parameters and a pair of non-parallel direction vectors, we're going to have a plane. All right, so it's kind of a very natural extension of the notion of line into these higher dimensional figures, in this case, the plane. All right, so that's that problem. That brings it to a conclusion. Let's head back to the class notes. I want to work one last problem with you in this subsection. In this problem, a plane P in three-dimensional space is being described by three different position vectors, P, Q, and R. So as we work our way over to the document camera, you're going to have to ask yourself, if I'm given three position vectors, how am I going to generate two different direction vectors? Because we're going to want to find the vector and parametric forms of the plane P. In part 2 of this problem, we're told that one of the points that sits on this plane P has the form 4, comma B, comma 7. And what we're going to want to do is use those parametric forms of the equation of the plane to work out the missing coordinate B. So join me at the document camera to see the exciting conclusion and solution to this problem. All right, welcome back to the document camera. In this problem, a plane P in three-dimensional space passes through P, Q, and R. Find the vector and parametric forms of the plane, and then we'll work on part 2 once we finish part 1, but part 2 is asking us basically to find a missing coordinate. A point with coordinates 4, B, 7 lies on this plane. Find B. We'll see that that's a relatively easy thing to do once we've worked out the details for part 1. Now, in this problem, what we face is something, we faced a problem like this with constructing a line. What we'd really want is a pair of direction vectors, but instead what we have are three vectors that point to points on the plane. So let's just draw a rough picture of what we got. We have a vector P, a vector Q, and a vector R. And those are all pointing to points on the plane. So let's call it P, Q, and R. And what we really want, so we have to imagine the plane is kind of, suspended on those three tips. It's balanced on those three tips. Okay, what we really want, though, is a pair of direction vectors. And what we can do is we can just use these points, these vectors, P and Q and R, to generate some direction vectors. So let's think of one direction vector that we get by using P and Q. So we can take P and Q, let's take Q minus P, and we'll call that the direction U. And let's take R minus P, and let's think of that as the direction vector V. So then we can use P together with the two direction vectors to write out the vector and parametric forms of the plane. So that's our plan. All right, so let's get our ducks in a row. We've got P. Let me stack these on top of each other. That'll help us kind of do these calculations a little bit more easily. So I'll use P, Q, and R. I'll keep them stacked like this. So when I want to form our vector U, I'm going to take Q minus P, and we can work out the components of that. We're taking Q minus P, so our subtractions are going this way, so we'll have 1 minus 1 is 0. 3 minus 1 is 2, and 4 minus 3 is 1. So there's one of our direction vectors. And the other one we're calling V by taking R minus P. So now we're working with R and P, and we're taking our subtractions, R minus P. So we'll have 4 minus 1 is 3, 4 minus 1 is 3, and 5 minus 3 is 2. So there's our two direction vectors. And we can use this as our kind of position vector. That helps us put our plane in through a point in space. And this gives us our two directions to move in. All right, so find the vector and parametric forms of the plane. Let's put all our pieces together. So we can think of a generic point on the plane as having coordinates x, y, and z. And it's what I get by taking P and tacking on a multiple of U, so let's call that S times U, and a multiple of V. Okay? Now, if I collapse all of this, if I do the scaling and the vector addition, I can collapse that into a single vector, and it's going to be 1 plus 0s plus 3t. 1 plus 2s plus 3t. And finally 3 plus s plus 2t. And there's the vector form. That's a way of writing. I mean, I would think of either one of these as the vector form of the plane. And in parametric form, it would just be a matter of listing these out component by component. And in all of these cases, we're thinking of S and T as just being any points that we would want to choose from the real numbers. Just pick any pair of real numbers, S and T, plug them in here, and you're going to generate another point on that plane. So S and T can just run freely throughout the real numbers and generate points on the plane using these equations or these vectors. Okay, so we've got vector form, we've got parametric form. Now let's go to part 2. This is where it gets fun. We know that there's a point on the plane of the form 4, b, and negative and 7. 4b and 7. What does that b have to be if we know that this is a point on the plane? Well, we had a situation like this with our line. What we can do is use our parametric form. That ends up being, I think, the simplest form to work with. I can equate the 4 with this x, so 4 can be equated with 1 plus 3t, and 7 can be equated with 3 plus s plus 2t, and using those two equations, we should be able to find s and t, the values of s and t that are specifying this point, and once we have that those s and t values, we can come in and find the missing middle coordinate, which in this case would be this y coordinate. Okay, so let's just see what we're saying. We're saying, for this point, we know that 1 plus 3t has to equal 4, and 3 plus s plus 2t has to equal 7. All right, that's dictated by knowing these coordinates and matching them up with these representations of x, y, and z in parametric form. All right. Now let's take a look at that. Let's take a look at this system, right? So if I subtract the 1, this is saying 3t is equal to 3. And this equation is saying s plus 2t is equal to 4. So I can simplify this system by getting all the constants on one side and keeping the s and t on this side. Now, this one's pretty easy. This degenerated, right? I don't have a mixture of s's and t's in both equations. This one here is very simple. This says automatically that t is equal to 1. And if t is equal to 1, then by brute force substitution, I can see that s plus 2 times 1 equals 4, or s equals 2. Okay? So what do we know? We know that this point is being generated by t equals 1 and s equals 2. And now by plugging into this equation, I can get the missing coordinate b. So b has to be what I get by taking this equation, and in place of s, I'm going to write 2. And in place of t, I'm going to write 1. And so that says that b is equal to 1 plus 4 plus 3. So b is equal to 8. So our point must be 4, 8, 7. Okay? And so that's a nice way to put those parametric forms to use, right? If you know 2 of the coordinates, you actually do know the third by working out the value for s and t that's generating that point. Okay? All right, that brings a close to this problem.